Hello and welcome to the ME470 Tensile and Indentation Test Frame, sponsored by Bill King and built by this team. When researching and developing how to perform tensile and indentation tests within a robotic scanning station, we found that all commercially available units were too large for our application. The work envelope is fixed at 6.5 by 7.5 by 5.5 inches tall, as anything outside this envelope will collide with the scanner head. Beneath the base plate of the indentation test frame are the controls for this system. We will discuss this near the end of the video. When designing both test frames, we initially designed for machining metal components. Due to lead time constraints, we settled with a functional 3D printed prototype of only the indentation test frame. The indentation test frame consists of a 3D printed ball screw, two involute gears, a top plate, a base plate, and a set of twin linear guide rods. In the middle video, you will see the ball screws bearing journals being sanded into tolerance for a press fit installation into dual radial 3/8-inch ball bearings. On the right and left videos, we have specimens being compressed while recording load cell data. For the tensile test frame, we printed a low-fidelity prototype to verify line of sight from the laser scanner to the dog bone specimen being removed at this moment. The carriage moves in this prototype, but would be ball screw driven in the future. Here, we have the indentation test frame completing one up and down cycle while recording load cell data. If you listen closely, you can hear the stepper motor running. In the top left, we have the Python-based user interface that is running. This interface uses input data coming from serial communication via UART to plot a stress versus strain curve. The load cell and stepper motor positional data are being used to calculate the stress and strain. Note how the top and bottom plates deflect significantly due to being plastic instead of steel. Steel components will result in no greater than a 20,000th inch deflection under the maximum 200 Newton rated load. Here is an overview of the electrical component layout. A summary of project deliverables is listed on the screen. This project stemmed from a need for a more compact test frame due to the limitations on build volume via the robotic scanner work envelope. Both prototypes are capable of 0.78 micrometer indexable linear displacement through the use of a stepper motor, a set of involute gears, and a low-pitch ball screw assembly. We would like to thank our sponsor, Dr. Bill King, for sponsoring this project. We would also like to thank our advisory committee. We would also like to lend a special thanks to Professor Blake Johnson for the wonderful semester. Thank you.